In this project, we used machine learning and a combination of sensors to develop a simulated piano keyboard that users can play by merely moving their hands and fingers, without actually sitting in front of any keys. Our goal was to give people an embodied and interactive way to perform in an airband without the need for any musical instrument experience, in an effort to make the user feel as if the music was coming out of thin air. One of the feature extractors we used was a small microcontroller called a microbit, which consists of several integrated sensors. With this, we communicated with a machine learning program called Wekinator with a protocol called Open Sound Control.
One of the first things we tried to measure with the microbit was the distance between a user's hands, which would help us interpolate their relative position. We tried to use two of the microbit's embedded components, the magnetometer and the radio antenna, which we could use to measure the magnetic strength and the signal strength between a pair of microbits. Unfortunately, the magnetometer was too weak to provide useful data, and the radio signal strength measurements were far too sensitive to the orientation of the controllers, as shown by the variation of the green square here. So we decided to pursue video input with the Microsoft Kinect instead.
Unfortunately, attempting to integrate the Microsoft Kinect with Mac OS X was also a lost cause. While we got the depth view working, as you can see on the left here, the skeleton tracking functionality that we actually needed was not supported. Due to the issues with the Kinect, we instead decided to use the computer's webcam for video input and tried to track specific colors on the user's hands as an alternative to skeleton tracking. This allowed us to fluidly communicate with the computer and pull data directly into the web app.
To measure more precise finger motions that the webcam could not detect, we attached flex sensors to a pair of gloves. These flex sensors were connected to the microbit's input pins and transmitted analog voltage values to a radio receiving microbit that we connected to the computer. This was then trained in Wekinator and passed to the web app using OSC. After successfully classifying whether fingers were bent or unbent, we upgraded the gloves to be more conducive to color tracking. We knitted some brightly colored finger sweaters to not only be more easily identified by the camera, but to also more securely fasten the sensors to the gloves. Since we wanted to give people a unique musical experience, we developed a web app GUI that users could run to train the data themselves. With this training, we observed three main motions: whether the user was playing or not, the range at which the user played, and the notes played at that range. The notes the user played were determined by the flex sensors and were trained prior to running the web app with a nearest neighbor classifier. This is because the sensors did not vary from person to person. The app training begins with a horizontal threshold to classify if the user is playing or not. She is considered playing if her hands are detected below the threshold and not playing if above. The first step is to record her left hand below the threshold on the leftmost or lowest end of the virtual keyboard. When the user presses the right arrow key, this is repeated in the middle of the keyboard and at the rightmost or highest end of the keyboard to create a horizontal regression range. This regression is trained to determine the range at which the user plays as she moves her hands horizontally. After completing the recordings with her left hand, this process is repeated with the right hand, and then a scenario with no hands in sight is also recorded. Finally, this data is submitted to Wekinator for training. The top video shows a full view of the webcam's input, but the bottom grayscale video represents what is actually output to Wekinator. We reduced the input size to only capture where the user is moving her hands and avoid excess noise. Notice that the gloves light up when they enter the lower part of the frame. The app searches for a specific range of RGB values in each pixel and illuminates that value when it is identified. This shows her when and where her hands are recognized. We first trained the classifiers using decision tree.
Okay, so this is the decision tree and it's not changing anything.
Which, as you can see, did not work at all. So instead, we used nearest neighbor with 3 neighbors. This worked reasonably well, but was very dependent on a consistent environment. Any change in lighting or surrounding colors, such as clothing, heavily impacted the results. Because it's so much fun.
to now.
Try just bending like individual fingers.
Okay, then just that finger.